folks, so today we are talking more about collisions and how we can use ideas of momentum to predict how objects are going to behave both before and after a collision or an explosion. So let's get into it. So first of all, a little bit of review just to make sure that we're all on the same starting page. So when we talk about momentum, momentum is a vector quantity meaning that momentum has direction and can therefore be negative. And we can calculate momentum using this equation. Momentum, or P, is equal to mass times velocity. So the direction of momentum is the same as the direction of velocity. We've also talked about ways to change the momentum of an object using this idea of impulse. So if we multiply the force exerted upon an object by the amount of time that force is in contact with the object, we can calculate how much that momentum will change. And as a reminder, to calculate change in momentum, we just do mass times final velocity minus mass times initial velocity, assuming that the object doesn't change mass, which it usually doesn't, so that works out well for us. All right, so if we're talking about impulse and objects exerting forces on each other, there are three major types of interactions for us to be familiar with. The first type of interaction between two objects is elastic collision, which we can also think of as a bouncy collision. These are situations in which two objects collide and then bounce off of each other. Ergo, bouncy collision, okay? So an example would be if you've ever played pool, if you hit one billiard ball into the other one, they don't stick together, they kind of go off and do their own thing after they collide. That would be an example of elastic collision, right? Now the other option for collision is therefore inelastic collisions, which we can also think of as sticky collisions. So these are collisions where the objects hit and then they're stuck together and they move as a single unit after collision. So a straightforward example of that would be catching something. So you start off, you're here, a ball is coming towards you, you're interacting or you're behaving independently in that moment, but then once you catch the ball, you're going to move together. You are a single unit. So that would be an example of an inelastic collision. And then our third type of interaction isn't really a collision so much as like a collision in reverse, essentially, and that is explosion. Now, obviously, you think explosion, you think of explosives and dynamite and all that stuff, but for our purposes here, an explosion is any situation where you have a single object breaking apart into multiple objects, okay? So throwing a ball, for example, we would classify here as an explosion because it starts off with you and the ball, you're moving together, but then once you throw that ball, you are now separate entities moving and behaving independently of each other. Okay, I know that's a less exciting explosion, but explosion, yay, okay, cool. So as we're talking about these objects that are interacting with each other, it becomes really important for us to be clear in terms of what we're focusing on, what objects we care about, and what objects we don't care about. So this brings us to the idea of systems. Now, a system is just a defined collection of objects, and we can kind of choose to create that boundary and draw our boundary for our system whichever way we see fit in a particular moment, okay? It's whatever collection of things we actually care about. I realize that's very vague, but we'll get some more practice with it. It'll make more sense, okay? Now, once we've defined our system, we've identified which objects we care about that we're really focusing on, there are two major types of systems that we might have on our hands, okay? An open system is a system of objects where those objects are affected by outside sources, okay? So, anytime when there's something else that's sort of coming in outside the system and hitting it, exerting some sort of force on it, pulling on it, now we've got an open system. Our objects are now subject to the effects and interactions of things outside that defined collection that we're really focusing on. In a closed system, essentially our objects are isolated. They can interact with each other, but there's not going to be any interference from any forces outside that system. It's really just those two objects operating together, but like without the influence of anything else outside. Okay. So to give you an example of this, say we're going back to our pool table, all right? A cue ball collides with an 8-ball. The 8-ball starts off stationary. It's on a level pool table, and maybe we say our system is just the cue ball and the 8-ball. Those are the two objects that we are interested in, so that's how we're defining our system. So my first question is, based on this information and what you know about the world. Do you think this is a closed system, or why not? Well, I'm going to say this probably is not a closed system in reality, because if you've ever felt a pool table, there's a pretty significant amount of friction. So our two billiard balls in this situation are going to be influenced by the force of friction from the pool table. And since the pool table is outside of our defined system, that means we have outside interference, and therefore this is not a closed system as described. Now, if we instead took our game of pool over to a level, frictionless surface in a vacuum, now would we have a closed system? At this point, I would say, yeah, probably this is a closed system if there's truly nothing else there, no friction, no air resistance, no nothing. This is now a closed system. I recognize that true closed systems are kind of hard to come by then in real life, but a lot of times if there's low enough air resistance, low enough friction, we can sort of approximate a system to be closed, even if it's a teeny bit open. And that's okay. All right. So let's continue to imagine this collision here. So we've got two objects colliding with each other. We know each object is going to experience a force from that collision. Question for you, which object is going to experience a greater force from collision? Well, thanks to Newton's third law, we know that both objects have to experience the exact same force. Forces always come in equal and opposite pairs. So when these two objects collide with each other, object 1 is going to experience this force to the left from that collision. Object 2 is going to experience a force to the right, but those forces are equal in magnitude. They're equal in size. Okay. So we know then that these two objects experience equal and opposite forces from this collision. It's also safe to say that the collision lasts for the same amount of time for both objects. It's not like one is colliding for longer than the other. They both experience the same time of collision. Now, according then to the impulse momentum theorem, what must be the same for both of these objects? Well, if the force is the same, and the time of collision is the same, then according to the impulse momentum theorem, both objects must experience the same change in momentum as well, just in different directions because they're experiencing forces in opposite directions. So object number 1 experiences a change in momentum overall to the left because that's the direction of the force. So if that object had a momentum to the right, that momentum would decrease. If that object originally had a momentum to the left, then that momentum would be increasing. All right. And then similarly, object 2 then experiences the same change in momentum because it's the same force and the same time, just that change in momentum is directed to the right instead. So here's what that means. All right. During a collision or an explosion, some interaction between the objects, those objects are going to transfer momentum back and forth to each other. One might give momentum to this one, and then as a result, it loses it, or the other way around. But either way, there is a transfer of momentum, but we don't lose any momentum. The change in momentum for one object is the same as the change in the momentum of the other object, just in opposite directions. So what this means is that for a closed system where we have no other forces acting on our objects, the total momentum of all the objects has to stay the same. It doesn't matter how those two objects within the system are interacting, whether they're colliding, exploding, whatever it is that they're doing, as long as it's a closed system and we don't have any outside interference, that total momentum gets passed back and forth, but the total does not change. So this brings us then to the law of conservation of momentum, which says within a closed system, the total initial momentum prior to the collision or explosion of all the objects in our system is going to be equal to the total combined momentum of all the objects after the collision or explosion. If we want to write that out mathematically, what we can do is write something like this, that the sum of all the initial momenta, and this little funny E thing, that's a Greek letter sigma, which just means sum. Okay, so if we add up, if we sum all the initial momenta of all of our objects, that's going to be equal to the sum of all the final momenta of all of our objects. Okay, so to give you a more specific example of that, If we had, for example, two objects that were colliding elastically with each other, in other words, they were bouncing off of each other, then the mass of the first object times its initial momentum, or initial velocity, excuse me, plus the mass of the second object times its initial velocity is equal to the mass of that first object times its final velocity plus the mass of the second object times its final velocity. So in other words, the initial momentum of our first object plus the initial momentum of our second object is equal to the final momentum of our first object plus the final momentum of our second object. They might pass momentum back and forth between them during that collision, but the total amount remains the same. So let's do a quick check for understanding just to make sure we've got all this. Say we've got a 5 kilogram cart on a frictionless track. It's rolling at 2 meters per second to the right. It then collides with a 3 kilogram cart that is stationary, and both carts stick together after the collision. First question, what type of collision is this? Since both carts stick together after that collision, we know this must be inelastic collision. Right. Second question, do the two carts constitute an open or a closed system? Now, assuming that there's no other outside things interfering, we're going to say air resistance is probably not a big deal because we pretty much always ignore air resistance in this class. Since it's a frictionless track, there's nothing else interfering. This is pretty much a closed system. Third question, what is the system's momentum prior to the collision? Well, prior to the collision, our 5 kilogram cart is moving at 2 meters per second to the right. So we multiply those together. 5 times 2 gives us 10 kilogram meters per second to the right. And the 3 kilogram cart is stationary, so it has no momentum, which means that our total momentum just comes from that 5 kilogram cart, and it has a momentum of 10 kilogram meters per second to the right. Fourth question, what is the system's momentum after the collision? Now again, since this is a closed system, there are no outside forces interfering with our objects in the system. So that means that total combined momentum of both objects in the system has to be conserved. Or in other words, total momentum is still 10 kilogram meters per second to the right. Final question for you. If instead of sticking together, these carts bounced off of each other, would that change the final momentum of the system? So if the carts bounce off of each other, this would now be elastic collision. However, it would not change our answer because momentum is always conserved in all collisions, all explosions, any sort of interaction within a closed system. All right, that's all. Hope you learned something about collisions.